Okay, I think this is going. So, hello everyone. I am going to be walking through the worksheet that you guys weren't supposed to be able to find, but I've modified it so it's half decent if you want to follow this video as a method for analyzing your fly data. So, we're going to start by just looking at genotype frequencies, right? So, back when we started this experiment, and let's make this clear from the start, we're calling big A our wild type allele. We're calling little a our mutant type allele, and P is equal to A, and Q is equal to little a. P is equal to big A. So for big A, we only included homozygous flies for this experiment, and we only included 20 of them. So out of 100. So we know that our frequency of big A is 0.2. And we know that the other 80% of our flies were homozygous recessive. So that means we have 0.8 in terms of genotype frequency for little a. And if we want to double check if this works, we can add these up and they should always add to 1 because we're looking at frequencies here. So if we don't know the actual alleles that we had in our population, and we don't for any other generation, we have to use a different method. So I'm going to be using this last group. This is some data I just made up, so don't follow this word for word. So we are going to find our Q squared frequency using our vestigial fly count. And all we have to do is divide our vestigial fly count by the total amount of flies in the population. So this is equal to Q squared. And this number can be plugged in right over, copy, right here. Okay, so now that we have Q squared, which is equal to little a in our Hardy-Weinberg formula, we can find P. Actually, we have to find Q first. So all we have to do for this is find the square root of Q squared, and that gives us Q. And to find P, all we have to do is equals 1 minus Q. And now we have Q and P. So like we did earlier, we're going to do equals P squared. Don't worry about my emails. They don't show up here, thankfully. And then we are going to do equals 2 times P times Q. And if all is well here, we should be able to add these up and see that they're equal to 1. Perfect. Okay, so now we have a starting spot for our final observed population. And we know their allele frequencies, or their genotype frequencies, sorry. So if we go down here, observed for all of these is just going to be equals big A, right? Because we're in big A and we're looking at observed, times our observed final population total. And this will give us how many homozygous dominant flies that we have. We will also do this for hets and for homozygous recessive. Equals this times 470. And this should all add up to another 470 if I didn't mess up. Okay, perfect. So now we want to find our expected genotype frequencies under Hardy-Weinberg equilibrium. So under Hardy-Weinberg, we expect no change in allele frequencies over time. So Q should still be equal to 0.2. P should be equal to sorry, I messed this up. P is 0.2. Q is 0.8. There we go. So now we have to find our expected frequencies if we were to translate these into a randomly mating population where they can form hets. So we'll just do equals, well, we'll start with big A. Equals 0.2 squared equals 0.2 times 0.8 times 2. and equals 0.8 squared, right? So q squared, 2pq, and p squared. And then we'll do the same thing. So equals big A frequency times 470, because we need to compare the same population size, equals our Hep frequency times 470 equals 0.64 times 470. And now we add these up again just to make sure. And we should have 470. Nice. Okay. So now we have values that we can work with down here in our chi-squared table. Except these are flipped. Sorry for my slowness. It is the morning. Okay. So I've laid this table out. So all we have to do is follow the calculations it tells us to do above, right? So all we're going to do equals observed divided by expected, equals the same numbers squared, right? Same numbers squared, so equals this, divided by expected. And then we're just going to do this for every single one of them. And we can add up our final value of all of these here. And this is our chi-squared value. So we can use this value to compare to a chi-squared table. So a chi-squared table, I have my rules written over here. If our chi-squared value is greater than 3.841, then we have a p-value that is less than 0.05. And that means we are following Hardy-Weinberg equilibrium. Vice versa, if we have a p-value that is greater than 0.05, our chi-squared sum is less than 3.841. And we reject Hardy-Weinberg, and we can say that evolution is occurring. So you'll be using the same method to find your chi-squared values for the populace model that we ran a while ago. So you'll take allele frequencies from each of those, or not each of those generations, but at least generation 4, where we want to predict what model is closest. We will do the same method where if we saw p is equal to, I don't know, 0.7, right? We can find out that q is equal to 0.3. And then we'll just calculate our big A, big A, little a, and little a frequencies again, and run the same thing step by step. So I hope this makes sense. And if you guys have any other questions, feel free to shoot me a message. See you guys later.